Okay, let's try out this first example together. So what we have here is a rod with a mass of 20 kilograms. And it's rotating at 5 radians per second. And a moment of 60 Newton meters is applied to the rod at this instant. We want to find the angular acceleration of the rod and the reaction at the pin when the rod is in the horizontal position. So how are we going to do this? Well, we're going to follow our procedure for analysis. Also, since that mass center moves in a circle with a radius of 1.5 meters, this is the mass center right here, moves in a circle right here, its acceleration is going to have a normal component toward the center, which is right here, and a tangential component that's acting parallel to the path, sorry, not parallel, tangent to the path. So let's try it out. First off, free body diagram. Make a nice little one. We have two components, reaction components at that point O. We have our weight pushing down, and we have our applied moment. And then this is going to cause a tangential component of the acceleration and a normal component of the acceleration, as well as an angular acceleration. Goodness. So then we write out our equations. So the sum of the forces in the normal direction is going to be equal to our mass times acceleration in the normal direction, which is equal to our mass times our distance to the centroid times our angular velocity squared. And all of that is going to be equal to my force in that direction. So I only have one force in the normal direction, and so that is equal to this component over here. And then I have my tangential component, and so what that is going to cause, some of the forces in the tangential component are going to cause an acceleration, which will be proportional to this. And I've got two components that are both going in the tangential direction. One of those is the weight, and the other one is the tangential component right at O. And so when I solve for that, well, actually I can't solve for that, sorry, because I don't know the angular acceleration yet. So I need one more equation. That third equation is going to be the sum of the moments about the point O right here. So when I do that, I'm going to get, it's the moment of inertia for that position right there. That's the parallel axis theorem multiplied by the angular acceleration. So if I plug that in there, and I can look up what the moment of inertia is for, the mass moment of inertia is for this thin rod, it's equal to the mass times the length squared over 12. Then you can write it as follows. So we plug that in there, we have an equation for it in terms of mass and length. And if we simplify somewhat, we get this down to mass length squared over 3. And we add everything in there, what we have is, okay, all of this put together, this moment of inertia, everything else, is going to be equal to this equation, where this is from our sum of the moments equation, this is our applied moment, and this is the moment caused by the weight. So solving those, we get our angular acceleration is 5.9 radians per second squared, where it's always radians, and our tangential component, plugging this back into our previous equation, is going to be 19 newtons. So that's it for this time. Just be very careful. Remember, you have applied forces which cause an acceleration of some sort or another, and you have to set those equal to each other in your equation. That's why you need your kinetic diagram. So thanks for listening. See you all later. Have a wonderful day. Bye-bye.